My name is Ben Lawler. I'm an associate professor here in the Department of Automotive Engineering at Clemson University. I've been at Clemson for about 4 years, and my research is related to powertrains and propulsion systems, specifically related to internal combustion engines and the processes that go on inside an internal combustion engine related to thermodynamics, heat transfer, fluid mechanics, and the combustion process itself. Clemson University's International Center for Automotive Research has the Viper GS Center, whose goal is to develop tools to help the U.S. Army with their research and development needs related to military ground vehicles. Our research work within the center is related to the propulsion systems for military ground vehicles and developing ways to improve their power density, efficiency, and reliability. If we can improve the power density, efficiency, and reliability of Army vehicles, then we can enable these vehicles to carry more cargo over longer distances without loss of mobility. We are developing experimental test facilities for engines of varying scale to try to match the varying scale of Army vehicles depending on their mission and role within the convoy. In addition to being demonstration facilities, these propulsion test labs provide experimental test results of high power density engines at extreme operating conditions and data for model calibration and validation.
In the world of computer models and simulations, there's always a trade-off between computational expense and fidelity. So it's important to develop various models with striations of fidelity as well as computational expense to help evaluate and design future military vehicles. The reduced order models are valuable for rapid design evaluations and optimization, even for developing optimal powertrain control strategies. We're developing a tool that would provide accurate predictions of the thermodynamic and combustion process of high power density diesel engines on a highly reduced order basis to help the Army with powertrain evaluations for vehicles of varying scale and mission. In addition to thermodynamics and combustion, this tool will include accurate predictions of piston temperatures so that we can help maximize the power density of these engines without overheating their pistons.
We are working here on high-fidelity, three-dimensional computational fluid dynamics and finite element analysis that can complement reduced order modeling and experiments by providing a deeper insight into the thermodynamics and heat transfer losses inside an engine. At Clemson, we have developed a co-simulation technique which uses the heat transfer losses predicted by the CFD as boundary conditions for the finite element analysis of heat conduction within the piston and vice versa with the CFD. This technique allows us to study the heat transfer losses from the combustion process of a high power density engine operated at extreme conditions. The finite element analysis can predict temperatures on a three-dimensional basis so that we can identify the local hotspots and their relations with the thermal limits of the piston material.
The newest showcase test facility that we've recently commissioned, we call the Hive, for Hardware Integrated Virtual Environment. The idea is that we will have digital twin models of military vehicles in the virtual environment. These digital twins will include as much accuracy as possible for the vehicle dynamics and the terrain environment associated with the vehicle's mission. For the propulsion system, we will use hardware-in-the-loop testing such that the engine will be physically tested on a dyno, and the remaining components of a hybrid powertrain can either be tested physically, including the battery pack and an e-motor, or they can be modeled in the virtual environment. We're excited to be part of the Viper GS Center at Clemson University, where we can use our unique test facilities and modeling capabilities to assist the U.S. Army with its mission to research and develop next-generation ground vehicles.